Welcome back to another HVAC-Engineering-Techie video. This is the channel that talks all things HVAC. We talk about engineering design, construction, equipment, systems, test and balance extensively, controls, efficiency, and system performance. These videos are intended to be educational in nature. They will definitely help you advance your career and help you on the job. Today's lesson is on tab air balancing of VAV systems. It's in conjunction with two other videos, T7, which is proportional balance, and T20, which is the balance of diversity systems. So those go in conjunction with this video. Before we go on and get started, I'd like to ask again, please become a subscribing member. It really helps me and I really appreciate it. It's absolutely free. It costs you nothing. It's painless for you. Just click the subscribe button down below. Give me a thumbs up if you like. That would help. And the reason is because Google uses that data to evaluate this video. So let's get started on VAV systems. The first thing we need to do is the pre-balance work that we do before we get on the site. And we need to do a pre-balance design review. The reason we want to do this is because we want to make sure if we see any problems in the design, we'll know what to do when we get on the site. So to fully understand how to balance a system, you must review the design. Look for, do all devices include supply, return, and exhaust grill indicating size, flow, and throw? If not, you actually need that information to balance. You're going to have to ask the engineer if that data is missing. Do flows of components match? Do the supply fan, CFM, the coil, and the filter CFMs all match? Do the return fan CFM outside of CFM equal supply fan CFM? Total flow of all connected terminal units match the supply fan CFM. If they do, that's great. Then you have a normal VAV system. If not, then you have diversity. Calculate air handler diversity affinity, and that is if you have more CFM in the VAV boxes than you do the air handler, is diversity. Total flow of all connected grills match VAV box CFM. Does the grills connected to the box match the VAV box? They need to. If not, there's something wrong. Review the design for system effects issues such as broken back fans, sharp transitions, or increase in duct velocity. Normal velocity gets lower the further from the system fan, at least it should. So system effect is where fittings or other things cause excessive pressure drop, like a broken back fan. That means just basically that a elbow turns the opposite direction of the fan rotation. Why that's important is because the air has to stop converting all this velocity pressure to static pressure and then turn the other direction and then regain velocity pressure, and that actually takes horsepower. So if you have a duct system that starts out at 2,400 feet per minute, goes to 1,800 feet per minute, goes to 1,000 feet per minute, all of a sudden goes back to 2,400 feet per minute, that's a problem because it takes horsepower to go up. It's free going down. So when velocity goes down a duct, the duct sides cause friction and slow the air down and actually converts the velocity pressure to static pressure. And that you get for free because that doesn't automatically. But when you need to go back from a low velocity to high velocity, that costs horsepower. And that's a problem. Special access areas are reviewed, such as sloped floors, very high ceilings, or obstruction to access. You need to make sure if you need something special, like a big lift to get to where you're going. To fully understand how to balance a system, you must review the system installation. So now you need to walk the site. And you should always walk the site before you start balancing. And in my company, it was always our policy that the supervisor or the foreman would go out and walk the site with the technician before he started balance, because normally they weren't actually ready to balance. Happens all the time. So as the air distribution systems are complete with air handling units, ductwork, terminal units, grills and diffusers, and dampers are installed per the design. It's bad when you've done a whole layout and you get to the site and realize there's a different number of grills and registers in the building than what was on the drawings, which means probably there was an addenda and they forgot to send it to you, which happens all the time. Now your layout drawings are wrong and they have to be redone on new drawings. That's really irritating, but it happens all the time. volume and smoke and fire dampers are 100% open. Remember, everything has to be 100% open for us to balance. Clean filters are installed. Fans have been started up and operating, free of vibration and rotating in the right direction. So if a fan is vibrating badly, then you operating it will damage it. So you don't want to do that. You want to make sure they fix them before you get to them, and they need to be operating the right direction. Now, you'd like to have them do that because it's running the wrong. If it's running the wrong direction, it's because they have it wired incorrectly, and you want to make sure they wire it back correctly. It's not your job to do that. You can do it, but it's not your job. You should have them do that. Variable frequency drives have been started up and programmed and complete. The safeties are verified and everything operates. The VFD is programmed, ready to run. Automatic temperature control systems are installed, programmed, and operational. Now, I know this statement is a perfect world. We never get on a job when the controls are 100% done, but they have to be done enough so that the air handlers modulate in automatic and all the VA boxes can operate in automatic operation, and you can set them up so you can make set point changes in both the air handlers and the VAV boxes. If you cannot do that through the control system, then they're not ready and you need to wait. Control software for the operation and calibrating controllers has been received from them to you, and that they've told you how to operate, unless you already know. If not, they need to train you on how to operate that. 8 HVAC systems have been started up and temperature control is being provided to the space. Is the mechanical contractor actually started everything up and is it running? Unfortunately, sometimes some mechanical contractors think startup means turn it on. It actually doesn't. There's a lot of things they need to do, and those need to be done before we get there. Ceilings are installed. Many times general contractors have asked us to balance a building with no windows, and you should not do that. You could probably do some work at the air handler level and maybe at the supply grill level, but the problem is it means you're going to have to remobilize later on when they're done to actually finish your balance, and that actually costs you money, so don't do that. Have them finish the building before you start. Building enclosure is complete with all windows and doors installed. That needs to be a complete envelope. We don't care about carpet, we don't care about paint, but we need to have everything that has a pressure barrier against it. It has to be 100% done. Suitable access for balancing devices and equipment is provided. If you can't get to something, you can't balance it, and you need to be able to get to it. So here's the general balancing process for VAV systems, irregardless of what kind of system it is. This is the basic, and then we'll get into the details, but this is the basic process. Determine if it has diversity. If the system has diversity, then refer to the balance process described in T-20, the tab of air and water system diversity. That explains it in a big detail. If it does not have any diversity, then verify all grills downstream of the VAV units have 100% open dampers and the air handler has clean filters. So when it means it doesn't have diversity, it means the total of all the boxes CFM equals the CFM of the air handler, or the air handler is larger than the connected VAV load. Then if you have that, you have a standard VAV system. In software, set all boxes to 100% open damper position. So you want to do this in software. So you just command the box to open the damper 100%. It knows how to do that, it's no problem, and it will stay that way as long as you have that command in place. Now, some people try to play with this different. You can actually go to the room sensor and set it down to 85 degrees, set it down to 58 degrees, and then go to the air handler and set it up to 75 degrees for the supply air temperature. And those dampers will stay open because the air is too warm to do any cooling. But I don't recommend that way, because if something changes, say the general contractor gets real irate because it gets too warm in the space and he makes somebody change that temperature, now your system's an automatic and it screws up your balance. You don't want to do that. Remember, we're trying to balance full flow of the air handler to full flow in the field at the same time. We don't want anything on automatic. We wanted a manual to do that. Lock the air handler flow to design flow by manually setting the supply and return fan speed at the VFD to the design flow plus 5 or 10%, something just a little bit more. So as you balance the field and we balance back up on the pressure, the CFM will go down, and you would like to have it so You verify the flow by pitot or the fan curve when you set up the air handler, so just make sure it has enough air for you can balance the system. Take preliminary balance readings for each box, listing them from the highest percentage flow to the lowest percentage flow. We normally do this by just running out and do a preliminary of all the grills, and that makes a preliminary of the box, and then you add up all the boxes, and then you know where you're at. Okay, begin balancing boxes from the highest percent flow to the lowest percent flow. Balance the box grills by either a series or proportional balance. And T7 will tell you how to do proportional balance. Now, what the difference is a proportional balance balances from the lowest box to the highest box with all of them, the percentages all being where they should be. So when you're done, if you change any CFM, it will automatically change, and you never have to go back. So if you balance the first two grills, you never have to go back to them. But in a series box, or no, a series air balance for grills and registers, you start with the highest percentage grill flow to the lowest percentage grill flow, and you balance down as you go, and you push air ahead of you. But the problem is, as you're pushing air ahead of you, you're also pushing air behind you. So what it means is if you do a job that has 20 grills, it really should be proportional. If not, you're going to have to run in circles for a while, because it will push the lower grills, but it'll also raise the higher grills. So if you balance the first two grills and you go through 10 grills and you go back to the first two grills, they're going to be higher flow than they were. And that's why proportional is always preferred. Number one for productivity, and number one for being the correct flow. So once a box is calibrated, leave it automatically tracking to design maximum flow. Record box calibration values and record the inlet static pressure at each box. So you're gonna get your list of your preliminary reads, and you're gonna start balancing at the highest box. You're gonna balance that box and calibrate the damper, so you're gonna calibrate the velocitrol so it knows where design flow is, and it can adjust that damper to give you full design flow. When you leave that box, you need to command the box from full damper open to command it to maintain the full supply air that you've balanced it to. So now that damper will stay right there where you balanced it, because you've commanded it to the CFM you want. And it'll stay right there, and that way you don't have to worry about it, and it'll always be the right flow. If you run low on supply air as you balance the last few boxes due to increased system static pressure, recheck the supply air fan flow and increase the fan speed to design maximum flow. If the fan is already at maximum speed, then recheck your diversity calculation if it had diversity. If it didn't have diversity and you've run out of air, then there's a problem somewhere. You got to figure it out, because if you got the design air coming in the system, you should be able to get design air going out of the system minus duct leakage. If you have a lot of duct leakage, you just may have to have more air out of the fan. Now, if you have fans that are operating less than motors, if you're operating motors at 1800 RPM or less, you can actually get more air out of that by speeding it up a little bit. I don't recommend you go very far, but you can go to 65 hertz, 68 hertz, something like that, and get a little more air out of the air handler if you need it. You just have to make sure you know how to do that, or you have the VFD guy help you do that. Complete balancing and calibrating all boxes. Remeasure the supply air duct static pressure. At this point, this will be the final supply air static pressure set point. You balanced all the boxes. They're all locked at maximum flow. Your air handle is locked. Look at the supply air static pressure, and that'll be your pressure set point. Return all boxes and VFDs to automatic control. So you're going to take all those locks off and just turn it back to automatic. Verify final supply air static pressure set point is in there and operating, and you're done. That's the way you actually do VAV balance. All right, general operating of VAV air handling units. Okay, this is a standard VAV air handling unit. See, it has a supply fan, it has a supply duct, and it has a bunch of VAV boxes down here that change the temperature in the room, and of course they change the temperature by changing the amount of flow. So this unit up here, you can see it has a preheat coil and a cooling coil and a heating coil. Now, how many coils you have and how they're arranged is strictly up to the design. You could get any combination you want. This has a full economizer and it has a return fan. Now, not all units have full economizers and not all units have return fans. It may have an exhaust fan in this relief fan. in this relief damper. I prefer return fans over exhaust fans. They're actually easier to balance. And remember, this is a 4-pipe unit. It has, I know it has 6 pipes, but it's really a 4-pipe unit. It has a preheat coil, a cooling coil, and a heating coil. And this arrangement, this cooling coil and heating coil allow us to do dehumidification, because we can cool the air and then reheat the air, keeping the space comfortable. We have a control system that has variable speed drives on the motors. It has a splier duct static pressure sensor. Actually, this one has a room sensor, pressure sensor. Has actual automatic actuators. We have a return air temperature sensor, display air temperature sensor. And of course, we have room sensors running these boxes. So what's the standard control of a VAV box? How does it operate? So a VAV volume box varies flow to the room to control temperature. With the velocitrol, there's a velocitrol right here, and it's a pitot. Basically, it's a ring pitot, and it's measuring the velocity pressure. And what it's doing is if the pressure increases upstream, and if you didn't have this, the more air would get into the room because the damper wouldn't know what's going on. But this velocity pressure sensor, if it gets more pressure, the velocity pressure rises, it will change that damper to maintain this flow to a constant flow. And that's why we call them pressure independent, because it doesn't matter what the upstream pressure is within reason. It has what its minimum maximum pressures are, but with anywhere within reason, it will do its job and make it independent. Supply air is variable volume, constant temperature, because the air handler puts out a constant temperature. Hot water electric recoil if heating is desired at the box, if reheat is desired. Sound attenuation if desired. A typical control sequence. Now, I'm showing the typical control sequence here just so you get an idea how it operates. This is not an exact sequence. It's a sequence I put in here just so you understand how it works. A real sequence would be a whole bunch more complicated. Room temp sensor modulates the VAV damper and hot water coil valve to maintain room temperature. Supply inlet velocity sensor maintains constant flow during inlet pressure changes, making the terminal unit pressure independent. Now, most people think that the room sensor controls this damper, but it's really not true. The velocitrol controls the damper, and the room sensor just resets the velocity pressure. If it wants more air, it wants to go up in velocity pressure, and so it'll control to that. And it doesn't make any difference, but that's how it actually works. Okay, balancing standard VAV terminals. Okay, verify all grills and balance dampers are 100% open. I know you guys are hearing that, but that's the first thing you got to do is make sure everything's open. Set the box damper to full flow. Lock damper into position in software so it does not modulate. Pre-read the flow of all connected grills to obtain total flow at present box damper position. List the grills in order of % of flow to design, which with the lowest at the top and the highest at the bottom. Perform a proportional balance. And again, see T7. If you're going to balance the grills by series method, then list the grills in order of % of flow at the design with the highest at the top and the lowest at the bottom. But remember, you're going to have to read these several times because as you balance a grill, you'll be raising all the other grills. That's why we prefer a proportional balance. Re-verify the total flow once balanced and follow manufacturer's instructions on entering the correct calibration factor into the damper controller to properly calibrate the damper to the flow you have read. At this point, the box is properly calibrated. Set the box flow to minimum cooling flow position and verify the flow. Set the box flow to minimum heat position and verify the flow. Now, sometimes we have, in our jobs, had set the box flow to minimum and actually reread the grills. And the reason is because some grills dump air. They don't work well with VAV systems. They're designed at maximum flow, and they're such that when you go to minimum flow, instead of distributing less air, they'll just dump it right down in a straight line. And if that's the case, reading the grills at low flow is helpful. Otherwise, it doesn't make a difference. And then set that heating flow. And we have never actually read heating flow, but you could. It just makes the form really complicated to have full preliminary flow, full flow, minimum flow, and heating flow. Would be lots of flows to have on a form. The box has hot water heat, set the balance valve to proper flow. It has electric heat, verify operation, and record inlet and outlet temperatures. Please actually check the temperature of the change of the air. A lot of guys will just check to make sure the control relay had been drawn in. So when it goes into heat, the relay clicks, I'm good to go. Well, that's not good, because you need to test the system to make sure it operates. That's part of your job. And if you didn't test that and it doesn't actually work, you're going to be blamed for that because you didn't look at it. So it's simple. Just make sure you know the temperature rises in the duct. We don't really care what the temperature drop is, but we want to show the engineer that we turned it on and we got a temperature rise. And that's what we want. Record maximum cooling flow CFM, minimum cooling CFM, maximum heating flow CFM, and heating box CFM. Box calibration factor and heating inlet and outlet temperatures. Now, your box definitely will have a maximum cooling flow set point calibration factor. Most boxes will not have any others. Some will. Some may have minimum cooling set point factor that you have to actually input, and some might have a heating flow CFM. Now you'll input the heating CFM because that's off the drawing, and you'll input the heating CFM, but you won't calibrate the box at those values. You just calibrate the box at the maximum value. You need to see what kind of controller you actually have on the job. Best practice is also record the inlet pressure to assist in future repeatability readings. You want to make sure you know exactly what that static pressure is. Now, I know that the unit's locked, but it could be changing as you test and balance. So if you got a repeat reading, you want to make sure you have the same static pressure you had before, or else it may not repeat. Okay, there's more than one kind of box. That other box we were looking at is just a standard VAV box. This is called a series fan box. And a series fan box, supply fan is on when the unit is in the occupied mode. So this unit has a regular VAV box right here, the valve, and a controller and a ring pitot. Then it has a fan down here in series that pushes the air out to the space. And then it has an inlet from the plenum with a filter on it. So the way these work is this fan, when we're in occupied mode, the fan comes on and the box wakes up. And this fan flows constant flow like this until this damper opens. When this damper starts open, it takes air from here and here if it needs it. So this fan is making this system some constant volume, but it's also using the heat from the plenum to heat the space. So the plenum is heated up with people, load, lighting load, electrical load, plug load, all that stuff, and it can use that heat, but it's a series fan. The main purpose of these is on a VAV system to make this not VAV, to make this constant volume. Supply air is constant volume of variable temperature. And why do we need a box that's constant volume? Well, some rooms can't have an air change difference, maybe because they have a pressure differential they have to have. Or maybe there's a code restriction, like a bathroom. It needs to, bathrooms are designed to have a negative pressure, and you can't have flow into them that changes that. More flow, you can have less flow. Or you might have sterile rooms or something like that in a hospital that have to have a constant pressure differential. In that case, you don't want VAV because it can mess up stuff. So we'll have a constant volume. You can have a hot water electric reheat if you want. You can have a sound attenuator if you need. Now, its sequence is similar. Room temperature modulates the VAV damper and the hot water coil valve to maintain room temperature. Supply inlet velocity sensor maintains constant flow of air while valve during the inlet pressure changes, making the terminal unit pressure independent. The terminal unit fan runs when the unit is occupied mode, providing constant flow, variable temperature to the space. Because when we need to lower the temperature, this valve opens up and provides cold air into the space. All right, so how do we balance this monster? Verify all grill balance temperatures are 100% open. Balance the fan flow to set the box design. So you set this fan up, and this fan normally comes with low, medium, and high speed. And you set the speed up just a little, so you have a little bit more air than you need, and you go out and balance the grills. At that point, the box is actually balanced. Set the box damper to the box return air bypass flow is neutral. So then what you do is you go in here and you open this damper until there's no flow in or out of this opening here to the plenum. that makes this air equal to that air, so you know that all the air coming in is going out this fan. And you need to do that to calibrate this box. So you got that. You've got equal flow. Then you read the flow on all connected grills and obtain the total flow present at this box damper position and this fan at full flow. So once you balance the grills, then re-verify total flow once balanced and use the manufacturer's instruction to calibrate this box, because it's got the total flow going. The total flow here is the total flow here, so now you can calibrate this box. At this point, the box is calibrated. Set the damper flow to minimum cooling flow position and verify flow by a pitot or DP from the box ring. Okay, because this once you set this at minimum, you no longer can take the grills or a pitot here to be flow. It has to be flowed just at this damper, and you can go ahead and cut into these tubes as long as you put a T in there with a plug and cook it up to your instrument, and you can read what this pitot says, or else you could do a pitot of this incoming duct, one or the other. The back box has hot water heat, balance valve, proper flow. Has electric, test the heater. Record the maximum flow of the fan, the maximum damper cooling flow CFM, the minimum damper cooling CFM, and box calibration factors, heating, inlet, and outlet temperatures. Best practice is also read the inlet box static pressure for repeatability. So here's the third kind of box, a VAV parallel terminal unit. And a VAV parallel unit is different than the series box. Still has a fan, still has a VAV box, but it's not in series. This is in parallel. So this fan only runs in heating mode. In cooling mode, it's a standard VAV box. No difference. So parallel variable volume box. Supply fan is on only when in the occupied heating mode. Off when it's in cooling mode. So when it's in cooling mode, it's a standard VAV box. Velocitrol provides pressure independent operation. Uses interior heat from the plenum. So it's just like the other box, it will take this heat from the plenum and use it to heat. And we normally use these for perimeter heating boxes. So they provide an efficiency in using the plenum's heat. It's an economy kind of thing because we get to use some heat that's already in the building we don't have to pay for. Fan induces plenum return air when in the heating mode. Supply air is constant volume in heating mode and variable volume in cooling mode, because the fan's a constant volume device. When it's on, it's a constant volume. When it's in VAV, it's variable volume. You have an electric heater or reheat coil if you need, or sound attenuator if desired. Typical control sequence. In the cooling mode, the room temperature sensor modulates the VAV damper and hot water coil valve to maintain room temperature. The fan is off. Supply inlet velocity sensor maintains constant flow of the air valve during the inlet pressure changes, making the terminal unit pressure independent. In heating mode, the unit fan is on and the hot water coil runs to provide heat. The damper is at minimum position, providing ventilation air or heating CFM. So how do we tab this monster? 1. Verify all the grills dampers are 100% open. Set the box damper to full flow with the fan off. Lock that damper into position in software so it does not modulate. Reread the flows of all connected grills to obtain total flow at present box damper position. Balance all grills by the proportional or series method. Proportional preferred. Follow manufacturer's instructions on entering the correct calibration factor into the damper controller to properly calibrate the damper to the flow you have read. At this point, the box is calibrated. All right, set the box damper flow to minimum cooling flow with a ventilation flow position and verify flow. From a duct pitot or from the box ring. If the box has hot water, set the balance valve to proper flow. If it has electric heat, verify operation and record inlet and outlet temperature. Record the box maximum cooling flow, minimum cooling flow, box maximum heating flow CFM, box minimum flow CFM, and maximum fan heating flow CFM. So you got to read the valve, the air valve, for both heating and cooling maximum minimums, and then you're going to read what the fan does, and put these in your report. Box calibration factor and the heating and inlet outlet temperatures. Best practice again is to always record a static pressure upstream. All right, this is the VAV air handling unit that's providing air to those boxes we just looked at. So a typical control sequence, a supply fan and return fan shall run and the outside air damper should be at minimum position anytime the system is in the occupied mode. So when we're occupied mode, both fans run and this minimum outside air damper opens to provide ventilation air. So this unit is a little different. It has a full economizer, but it also has a minimum outside air damper there to provide flow when we just need ventilation air. And the reason is this is a big unit. These dampers can be very, very large, and they can leak more than your minimum ventilation. So they're called low leak dampers, but that's in contrast to a standard damper that you can actually see through. So these have minimum, and they have a flow meter on it normally, and that allows us to keep this minimum CFM all the time. Because remember, this is a VAV, and as these fans change, there's a possibility this pressure could change, and then we have less air here, so this damper may have to open up as it slows down because the ventilation air is a constant. We don't want a variable volume. So modulate the supply fan speed to maintain the supply deck pressure. So here's a pressure sensor. We want to maintain the supply in the supply pressure in the supply air duct. Modulate the return fan speed to track the supply fan speed, offset by the CFM required to maintain building pressure, and modulate the relief outside and return dampers to maintain building pressure if the minimum doesn't do it by itself. Maintain the minimum outside air damper to flow set point. So basically, this fan speeds up to maintain this duct pressure, and this fan tracks it but by less than whatever our minimum outside air is. So whatever that outside air requirement is, this fan will be lower than it. And that's why it's important for fans within air handlers be the same type of fan, that they have generally the same curves. They don't have to be the same size, but they need to have the same curves. So when this slows down, it will be at a certain percentage of flow, and when this one slows down the same, it'll be the same percentage flow. Otherwise, this gets impossible to do the tracking. You have to do tracking then by flow or pressure. You can't do it by fan speed. Fan speed is by far the easiest, as long as the fans are the same kind of fans. So you have to, this could be a centrifugal fan, this could be a centrifugal fan. But if this is a plug fan, and this is a centrifugal fan, you're going to have a problem. And certainly if this is a vane axial and this is a centrifugal fan, they'll never match on the curve. So basically it needs to be the same kind of fan. And then if this minimum air won't maintain building pressure, then this thing takes over, and it will then start to open a bigger damper to get more air in here. Or if the pressure is too high, then it will speed this fan up a little bit and open that damper a little bit to relieve some air. So this means we can control building pressure exactly. Modulate the hot water valve. This is the preheat valve to maintain the preheat set point temperature 45 degrees measured at the heating side of the cooling coil. So right here we have a temperature sensor that measures the leaving temperature of the cooling coil, which normally a set point is 44 or 45 degrees. And then we have a heating coil downstream, and we have a sensor down here to measure the temperature here. So this coil is designed to preheat the outside air up, because if it's 20 below zero, we don't want that cold of air coming in and hitting a coil. It'll freeze up a coil. So what they do is we want this thing to maintain 45 degrees measured right there. And we can do that because that's the set point of this coil. So this heat here heats it up to whatever the cooling set point is, so then we don't waste any energy. And if it needs more heat, this coil can put in more heat. So that, and if it gets too cold, if this measures 38 or below, then it closes all the outside air dampers, turns off the fans, and opens the heating coil and chill water coil, and maybe the heating coil, but normally these two, and it opens them up and sends a freeze alarm because it's getting ready to freeze. If we can't maintain that 45 degrees here, this coil will start to freeze. So basically, something's wrong. Probably this coil has stopped flow, and it's too cold outside, so it's getting ready to freeze this coil, and so we'll go into a freeze operation. Modulate the chill water valve and the hot water valve to maintain the supply air temperature set point. So these two come on to measure that set point. So if the outside air temperature between 45 and 70 and the outside air temperature is 10 degrees below the return air temperature, enter economizer mode and modulate the outside air relief and return air dampers to maintain supply air temperature set point at the mixed air temperature sensor. The outside air and return air temperature equal, return to the normal operation. So in economizer mode, we're running flow to the space, and we notice that the outside air coming in is colder than the return air by 10 degrees. Now that 10 degrees is just a number. It could be 5 degrees, it could be 8 degrees, it could be whatever the designer and the control guy think it will operate best at. But you don't want to get them too close because then it'll hunt back and forth. So if we get air, then we're going to go ahead and open up economizer, which opens up this, closes this return air damper, and opens the relief damper. Now the return air and relief damper are always the same percent opposite. So they could actually be linked together, but the outside air cannot because we need it to operate when this is still open sometimes. So basically, this is closed, so all the air coming from the return fan is going out the relief. This is open, so all the supply fan air is coming in from the outside. So now we have outside air doing all the cooling. And we'll modulate that down. If it gets too cold, if we go drop below set point, we'll start closing these down and putting some return air so we can mix it here to get where we need to go. So this works fine. It's a standard economizer cycle. Reset the supply air temperature set point based upon connected load. Every 5 minutes, if any box damper is greater than 95% open and no box is less than a minimum position that are equal to minimum position, lower the set point 1 degrees. No box damper is greater than 90% open and one or more boxes are at minimum position, then raise the set point 1 degree. The reset range should be 55 to 70. So what we're doing there is we're resetting the temperature. Remember, this is a variable flow constant temperature system. And we're resetting the temperature for maximum benefit of these boxes, especially if you have some of them that have no heat. If all the boxes have reheat, this is pretty simple. If 2 or 3 or 4 or 5 have cooling only boxes, now you have to reset the supply air temperature or else you'll overcool those zones. You could have 60 degree temperature in this duct, and if this box has a 30% minimum set point because of ventilation air, you'll freeze. The room will probably get to 65 degrees. It'll be very bad, so you can't do that. If the room humidity rises above 60%, place the cooling coil into dehumidification mode. When the room humidity drops below 45%, return to normal temperature control mode. In dehumidification mode, modulate the chill water valve to maintain 55% cold deck leaving temperature and modulate the hot water valve to maintain the room temperature. Monitor all unit temps, supply air, and return air status. So what you're going to do is if this sensor's down here detect if it's 60% humidity in the space, then they're going to turn it into humidity. So they're going to drop the temperature in this cooling coil to start wringing moisture out. And then they're going to raise the temperature here with a hot water coil to keep our set point the same until the space gets below 45%, and then we turn it back to temperature mode. So that's a standard dehumidification mode. All right, so how do we balance this monster? So test the fan, water coil and hot water coil to verify operability. Verify the unit provides airflow and temperature air for both cooling and heating. Adjust the air handler fan speed and dampers to set supply and return airflow to the design value. So we're going to adjust the supply air fan and all the dampers to set supply and return airflow to design value. So this is going to have the minimum outside air. We're going to have this at design value, this design value, and we're going to adjust the fan manually. We're not going to do it in automatic. We're not putting any set point in the supply air duct. We've set these air handlers up manually. Lock the supply and return air fan speed to provide design flow CFM by manually setting the speed of the VFD to flow plus maybe 5% or 10%, because we're going to increase the flow by back, and as we balance, we'll back pressure up. If the system has diversity greater, if the system has diversity present, some boxes are closed to match the diversity flow. Balance and calibrate each VAV box by measuring actual flow and calibrating box controllers for the same flow. Box will have a maximum flow set point and may have minimum set point and heating flow set point, depending upon the controller functionality. See T-20 for diversity flow if it has diversity. Once each box is calibrated, set it to track the design flow in software. So basically, you went and you commanded the damper full open. Then you went and read the grills, and now you're ready to calibrate that box to a different flow than what it has, thinking it has at full open, because the box will be reading a CFM. It won't be right, it'll be reading it. Now you want to put a CFM so its reading will be correct, but what you're actually doing, is calibrating that velocity probe, the velocity pressure probe. So once you input that into the box, it is now calibrated, like we said before in the boxes. Measure unit flow by duct. When you're all done balancing the boxes, measure the unit airflow. Input supplier different pressure set point into the controls. Release all terminal units and enter to automatic operation. Now, like we talked about earlier in the VAV boxes, when you've got all those boxes balanced and calibrated, then the supplier duct pressure, remember our air handler is still locked, and once we get them all balanced, we read the duct supplier static, and that's our differential set point, and that's what needs to be put in here. Now we can return it to automatic operation. Adjust the balance valves and set the water coils flow. Balance outside airflow to provide building pressure set point and minimum ventilation flow at supplier design flow. Adjust damper linkage to provide any offset between outside and return dampers as required. So if we have to set some dampers, we can do that. Normally we want these off, so we should do everything in software. Record unit airflows, outside airflows, return airflows, relief airflows for both non and economizer mode. Verify building pressure is set point up for both operations. So when you get it balanced naturally and you have your ventilation set up for building pressure, then you need to turn on the economizer, see what happens at full economizer. It's really irritating when you have a building that runs fine and they turn on the economizer and it blows the doors open. It's because it's not set up for both. Now, sometimes that's a problem for a balance guy. Now this one has an active supplier pressure, a building pressure sensor, which is great because you can have this now control that so that won't happen. But if you don't have one of those, then you need to adjust things so it's a little bit both ways, but you remember, you must have a minus pressure here and a positive pressure here, and this needs to be zero pressure. Otherwise, you can't get it, because this has to be minus pressure to get ventilation air in. This needs to be positive pressure to get relief out of the building. And if this fan is overpowering this fan, and this is negative and this is negative, then you have three inlet dampers. If this fan is overdriving the supply fan and both these are positive, then you have two relief dampers. So you have to balance this so this is zero pressure. Now it's pretty easy during economizer because this damper's closed. And when it's closed, you don't have a problem. But when it's modulating, you may have a problem. So you have to make sure you can do that. Now in this one, where we have a pressure sensor, no problem. But when it doesn't, you have to balance them in both positions. Record leaving and entering duct air pressure for both the supplier and returner fans, filters and coil pressure drops, and the cooling water flows. Okay, now this is a basic operation of a dual duct, a VAV dual duct air handling unit. Now in the constant volume session, we talked about these, but the difference was in a constant volume, it only has one supply fan. The VAV, it has two supply fans, one for the hot deck and one for the cold deck, so they can run at different speeds. So that's what makes these different. It's still just like the other system, it has heating coil and chill water coil, and it has two ducts that run down through the building. And we have two VAV boxes in every room. One's a hot deck, one's a cold deck. And they either the cold deck provides 100 air, the hot deck provides 100 air, or they mix air to give what temperature they need in the room. So it has a control system. It has a supply duct sensor on each supply duct, so it can modulate these VFDs separately. And of course, it has a pressure sensor, just like the other one we looked at. And that's the system. So now the control boxes, the VAV boxes on a dual duct VAV are different. Now in a constant volume one, and in the older days, we had one damper shaft, and we had a damper here and a damper here that were opposite. So when the cooling valve was open, heat deck was closed. And then as you modulate damper, you mixed them. And that was natural, and that was pneumatic controls. They weren't very smart, but that does work well. Well, in a VAV now, we have two full VAV boxes with minimum set points and maximum set points because they can operate independently. Varies flow between the cold deck and hot deck to control room temperature. The Velocity provides pressure independent operation for both boxes. So each one of these has a pressure independent. Now, if you remember on the constant volume, it had just one pitot downstream running both boxes. So they were both set to a downstream pressure sensor. These are both upstream because they're totally independent. Supply air is variable volume, variable temperature. That's what makes this difference. In the constant volume one, the supply air to the room was constant volume, variable temperature. Well, in this case, they can be variable volume and variable temperature. Now, why they're doing that is it can make this system a very efficient system and a very good system. However, it's really expensive because of these dual ducts running through the space. You can have a sound attenuator if you desire. And this is where it's different. Here's a little control diagram of these boxes. So when it's cold, the heating box is full open. As it gets warmer, it closes to a minimum flow. And this is heating side ventilation air. And then when it starts to get hotter, the cooling box has been on for ventilation air. It starts to get, the valve opens up to cool the space. And that's kind of clever. Now, you can actually program these to have the ventilation air come totally by the heating side or totally by the cooling side, or like this one, which splits the minimum ventilation air 50-50 both cases. And that's what this 50% means. It means it's 50% of ventilation air, not that it's 50% of box flow. It's just 50% of ventilation air. Pretty clever. It does work very well. I've installed many of these systems, and they're pretty forgiving for operations. So the room temperature sensor modulates both the cold deck VAV damper and the hot deck damper to maintain room temperature. Minimum ventilation air should be through both the cold deck and the hot deck dampers at 50% of total minimum flow. Both dampers operate in full VAV mode for variable volume, variable temperature to the room. So how do we balance one of these then? Okay. Verify all grill balance dampers are 100% open. I know you're getting tired of that. Set the cooling box damper to full flow. Lock the damper into position in software so it does not modulate. Lock the heating box damper full close to its minimum ventilation CFM. Now what we're going to do is we're going to balance and calibrate the cooling boxes first. And the reason we're going to do that is because it's kind of hard for me to tell you exactly the right way to do this because the system design kind of might mess it up. Because the designer has the opportunity here to make the heating side and cooling side different sizes. You know, in a constant volume one, they have to be exactly the same size. Okay, but in this one they don't. So if this is done in a hot climate zone, the cooling side could be 30-40% bigger, 50% bigger than the heating side, or vice versa. So that messes us up on trying to do these together. So we should just do one side at a time and then it'll be easy. It's no big deal, but it is something to think about. So pre-read flows of all connected grills to obtain total flow at present box damper position. List grills in order of percent of flow to design with the lowest at the top and the highest at the bottom. Perform a proportional balance of the grills. So now you've proportional balanced the grills downstream of the box. Set the heating flow to maximum flow. Once the cooling boxes are all done, now we'll do the heating boxes. Set the heating box flow to maximum flow and lock the cooling box full close to its main ventilation CFM. Set the box heating damper to match the full flow of the cooling box if they're the same size. If they're not the same size, then you have to set it to maximum flow of the heating box. Re-verify the total flow once, balance, and follow manufacturer's instruction on entering the correct calibration factor. So now you've calibrated the cooling box all on the cooling side. Now you're going to do the heating side on the heating side. Set the cooling box to minimum cooling flow position and verify flow. Set the heating box to minimum flow position and verify flow. So we're going to verify those minimum positions actually work. Record maximum cooling flow CFM, minimum cooling flow CFM, maximum heating flow CFM, minimum heating flow CFM, and box calibration factors. So we haven't done the air handler yet, but what we will do is we'll do the cooling side first and do the heating side first, enter the calibration factors, and when we have all the cooling boxes balanced, we read the supply duct pressure, because that supply duct pressure now will become the actual system set point, and we do the heating, we do the same, so we can get both sides, the supplier pressure sensors. Best practice is always to read the inlet of the boxes. Okay, so here's how this controls. Here we're back to the air handling unit now. So the supply fan and return fan shall run anytime the system is in the occupied mode. Modulate the supply fan speeds to maintain each supply air duct pressure set point. Modulate the return to fan speed to track the speed of the supply fan offset by amount equal to the minimum outside airflow. Modulate return air fan speed, the outside air relief, and return air dampers to maintain building pressure and ventilation airflow, just like the regular air handler. Maintain the chill water valve and hot water valve to maintain supply air duct temperature set point for both the cold deck and the hot decks. Reset the chill water deck. Okay, now both these will have reset on them again, just like a regular system. Reset the chill water deck temperature set point based upon the connected load. Every 5 minutes, any cold water deck box damper is greater than 95% open, and no cold deck box is less than is at minimum position, then lower the set point 1 degree. If no box damper is greater than 90% open and one or more boxes are at minimum position, raise the set point 1 degree. Reset range should be 55 to 70 degrees for the cold deck side. Reset the hot deck supply air temperature to return air temperature. That's what we're going to start at, return air temperature. So whatever, if it's 80 degrees, we're going to set this supply deck at 80 degrees. Every 5 minutes, if any hot deck damper is greater than 95% open, then raise the supply air set by 1 degree. If no hot deck box damper is greater than 80% open, and one or more hot deck dampers are at minimum position, lower the set point 1 degree. Reset range should be 80 to 120. And these ranges, you can make these ranges anything you want, but that's what we're trying to do. We're trying to make this unit economize by using the heat of the plenum air, the return air, or room air, so we can use some of that free heat up here if we keep this at return air temperature. And then if we need to trim it up a little bit, we can turn on the coil to trim it up a little bit. The outside air temperature is between 45 and 70, and the outside air temperature is 10 degrees below return air temperature, enter the economizer mode. So we're going to do that same thing we did with the other air handler. We're going to run an economizer mode. If the temperature drops, if the outside air and return air come close, then we're going to turn it off and go back to regular air. Monitor the room temperature, room humidity, supply, duct air, supply, and return status. Now, I didn't put it in this sequence, but this unit can also dehumidify. You can put a dehumidified mode that tests the room. If it has high humidity, it can drop the cold deck temperature and let the hot deck temperature be the reset in the room. It's no problem. This one would do that almost automatically, except you'd have to have a humidity sensor in the room to turn this into humidity mode, but you could do that. So how do we tab this room? Test the fan, chill water coil, and hot water coil to verify operability. Verify the unit provides airflow and temperatures for both cooling and heating. Adjust the air handler speed and dampers to set the supply and return airflows to design values and lock in place by manually setting the VFD speed. If the system has diversity, preset some boxes closed to match the diversity flow. Balance and calibrate VAV box by measuring action flow and calibrating box control for the same flow. Box will have a maximum flow set point and may have minimum set points depending upon the controller functionality. See T-20 for balancing system with diversity. Balance the cooling side first and then the heating side, calibrating all boxes and leave tracking to the maximum cooling or heating CFM depending upon which one you're doing. So once you've balanced a box, at each box, you command it to track to the CFM you've balanced it to. So it will maintain that because we need it to maintain that as we go do the other boxes. Measure the final unit airflow by duct pitot. Release all terminal units to automatic operation. Adjust the balance valve to set coil water flows. Balance the outside airflow to provide building pressure. Set point and minimum ventilation flow at the supply air design flow. Adjust damper linkage to provide any offset between outside air and return air damper as required. That'll need to be done in software, but record unit total airflow by 100% cooling and 100% heating. Outside airflow and return airflow relief airflow is for both non-economizer and during economizer operation. Record building pressure and verify building pressure at set point for both operations, both normal mode and economizer mode. Record leaving and entering duct air pressure for both the supply and return air fans, filter and coil pressure drops, and the coil water flow. So basically just like a regular air handling unit, the only difference is we got two supply systems on the air handling unit. So the balance is not any different than a regular VAV. Okay, this is a a different kind of a system, but I wanted to put it in case you run into it, you'll know how to deal with it. It's called a poor man's VAV system. It's a package VVT system. It's a variable volume terminal unit, but it doesn't use a VAV air handler, nor does it use a VAV package unit. It's a standard old package unit. That's why it's a poor man's VAV. What happens is because a package unit has to have constant volume across the coil, if you lower the CFM on a package unit below 20% of its maximum, and maybe even at that, it'll start icing the coil. And when the coil ices, it allows liquid to go in the return and slug the compressor. And on a regular old style compressors, piston compressor, it will scramble the reeds and break the compressor. If it's a scroll, it'll still damage the compressor. It's not quite as susceptible to slugging as a piston compressor. So what we have to do is we have to keep constant velocity, constant flow across this coil. So we're going to do a system, we're going to make this constant volume, but we want this system down here to be variable volume. Well, how we do that is we put a bypass damper in that's controlled by the air velocity here. So we want to maintain a constant velocity of return air, so we know this unit has constant volume. You could actually measure supply, but I don't recommend it. The turbulence is less down here, and it's easier to measure return. So we've had better luck with measuring put a velocity sensor right here and just maintain that damper to maintain velocity. It doesn't care what else happens in the system. All it cares about is we have full flow to this air handling unit. These boxes can open, close, doesn't really matter. It just modulates to keep the air handler at a constant volume. Now there is one thing that separates these from a regular VAV system, and that is this is a heating and cooling unit. So when this goes into heating, all these boxes need to change polarity. They need to go from a cooling box to a heating box. In other words, in cooling, if you need more cooling, you want more air. Well, in heating, if you didn't do that, it'd get opposite. In heating, if you needed more heat, it would shut the box down. So basically, you have to reverse it so that during heating, when it needs more heat, it opens the damper. So what we do is we have a controller up here, control system that actually sends a signal down to these sensors and tells them you are now heating boxes, which is the one thing that doesn't work well with this system. All the zones are either in cooling or heating. You can't have one in heat, one in cooling. Now you can put reheat coils on or strip heaters on these boxes so that any single zone could actually reheat. You could do that. Never seen one, but you could do that. You also have heating in the unit, so basically you get hot air down here during heating mode, during cooling mode. So that's a package VVT system. These were really popular 20, 25 years ago. And one of the problems that made them not work too well is each vendor came out with their own system, and they had some really squirrely designs. Some of them had, and the problem is that back then the digital controls were not near as far along as they are now. And so they had a hard time. So they put zone sensors out to override boxes and to control it. And it turned out that control basically bit them because it didn't work very well. And a lot of systems didn't work well, and so their popularity plummeted because their systems just couldn't operate. So here's how it controls. The supply fan shall run and the outside air damper shall open anytime the system's in the occupied mode. Modulate the unit bypass damper to maintain a constant velocity at the velocity sensor. Stage the compressors and strip heater to maintain the supply air duct temperature set point. So this is just like a regular VAV in that the supply duct controls the temperature. The supply duct temperature sensor supplies this unit. It's not done from here. Reset the supply air temperature set point every 5 minutes. Monitor all VAV damper positions. In cooling mode, if any damper is full open and no damper is at minimum position, decrease the supply air 1 degree. If any damper is full open and no damper is at minimum position, decrease the supply air 1 degrees. If no damper is full open and one or more minimum position, increases the supply air set point 1 degree. Range should be 55 to 70 degrees. That range could be anything you decide it is. In heating mode, if any damper is full open and no damper is minimum position, increase the supply air set point 1 degree. No damper is full open and one or more dampers at minimum position, decreases set point 1 degree, so it's exactly opposite of the other set point. I tend to get confused because I'm looking at hundreds of sequences, so I'm sorry, I apologize about that. Monitor room temperature, room humidity, supplier duct temperature, and supplier return fan status. Well, how do we balance this? It's actually pretty easy to balance. Test the fan, cooling circuit, and heating circuit to verify the operability, verify the unit provides airflow and tempers air for both cooling and heating. Verify if bypass damper works correctly to maintain constant velocity. That's the important thing to test. Adjust air handler for CFM. Set supply airflow to design values and all boxes locked in the full flow position. Measure unit airflow by a duct pitot. Balance and calibrate each VAV box by measuring actual flow of the connected grills. Leave boxes automatically tracking maximum CFM. Balance outside airflow to provide building pressure set point and minimum ventilation flow and supplier design flow. Release all VAV boxes to automatic operation. Cycle bypass damper to verify constant flow is achieved. Record unit airflow, outside airflow, and return airflow. Verify building pressure set point. Record heating and leaving duct air pressure for the supplier fan and the coil and filter pressure drop. So you're going to do a pressure profile of the unit, so you know what you got to supply. You got to drop across the fan, drop across the cooling coil, drop across the heater, drop across the filters, and an entering pressure here. Okay, so this is a control operation of parallel air handlers, which are normally VAV. And I'm not going to do a full thing here because these balance just like a regular deal, but there is a special problem here I wanted to make you aware of, so you don't have to suffer through this like I did. So if you have two air handlers that are running together for whatever reason, I mean, these could be staged, this could be first stage, this could be second stage. One could be standby, it doesn't really matter. Well, it does. A standby be a little different. And this is the normal way they're controlled. They have a supplier duct pressure set point, a controller, a VFD, and all the controls. This controller runs all the controls for this one runs all the controls for that one. And this looks really good, but it doesn't actually work. The problem is we have a supplier pressure sensor for both units. And because everything just cannot be exactly the same. So if this VFD speeds up just a tiny fraction quicker than this one, then this one is going to get all the pressure and this is going to get none. What happens, since the supplier duct sees pressure from both units, it takes whatever pressure it got and controls the unit to that. So if this one is lower than this one will take over and this one will ramp up to make up that pressure loss. If this one's low, it'll make it up and make it bigger. And pretty soon, this one will have 100% flow and this will be at minimum flow, which means it's at minimum cooling because the cooling coil's over here and the cooling coil's here, but that doesn't work. I mean, we had set these up and it'd be perfect. You know, in the morning we'd set them up to be perfect, come back the next day and one's 100% and the other's at minimum flow. And the reason is you can't use two static pressure sensors, you must use one. So this had to be retrofitted with just one sensor. We're going to have two. You can have two controllers, but one controller would have to be master and one would have to be slave, so that there's just one pressure sensor, never two, and it works fine. It's just something that we don't think about during design that has to happen. And loop duct is exactly the same. That's two air handlers. Now loop ducts are done normally to save space. Maybe they don't have big enough fan rooms in the floor. They have one at just each end of the building. But normally they're done so they can run just one fan when they have low load and then run two fans, so they save a lot of energy by just running one. Loop duct units have the same issue. So they can't have two pressure sensors. They can only have one. Now, some systems might have isolation dampers here and here, so they can isolate side. If that's the case, then you need to have two pressure sensors, one on each side, but in software, you need to disable one when those dampers are open. And you only have one pressure sensor when they're open. When they're closed, you have two pressure sensors. That's a complication, but you can have that. So the sequence is, air handler 1 should run anytime the system is in the occupied mode. Modulate the supply fan speed to maintain the supply air duct pressure set point. The supply static pressure set point is not achieved in 2 minutes. Start the second air handling unit and modulate that fan speed to maintain the supply air static pressure. Fan speed drops below 30% speed, stop air handler 2. And the way you balance these is the same. Both air handlers must be balanced together with both units running at design flow. So you got to balance them together. You can't, even though one may start up by itself, you still have to balance them together because at maximum flow, they're both running together. The VAV boxes are balanced and calibrated like any other VAV system. Diversity must be set up just like any other system. It's no different, but you're running both fans together because you got all the boxes to balance. And that's the end of VAV systems. I hope that wasn't too long. This is one of the longest courses, but hope you enjoyed that. I hope it helped. I appreciate you being a subscriber. Thank you for being here. Have a great day. I'll see you on the next one.